Hi. So let's keep talking about why nanoparticles are special and maybe fill in some of the details and mathematical gaps that we didn't talk too much about the other day. So in order to do that, I have to introduce a topic from thermodynamics and chemistry, and it's called the Gibbs free energy. So if you study thermodynamics, especially if you study thermodynamics and you study it within a chemistry major, they're going to talk a lot about this quantity. It's actually the work or energy needed to create something, or it's the energy released when you destroy something or break a compound. So the Gibbs free energy is much like a potential energy in that it's the change in the Gibbs free energy that's important. The overall value itself, much like a potential energy, is kind of unimportant. But during a process, that Gibbs free energy is going to change. It's going to go up or down. If it goes down, if the Gibbs free energy drops, in other words, if delta G is less than 0, then the reaction, the chemical reaction perhaps, or whatever other kind of reaction you're doing, that's going to happen spontaneously. Okay, so delta G less than 0 means it happens spontaneously. If delta G is greater than 0 for a process, that means that you would have to input energy or give energy to the system in order to get that reaction to happen. Okay, so you can look at the change in the Gibbs free energy during a chemical reaction or any other kind of reaction, and you can see whether or not a process is going to happen spontaneously by looking at that changing value. Now, you can define the Gibbs free energy delta G in terms of the change in the internal energy of the system from thermodynamics, which is delta U, and then minus T, the temperature, delta S is the change in entropy, plus P, the pressure, times the change in volume. So that's the equation for the Gibbs free energy change. If you remember your thermodynamics, that delta U, that change in internal energy, is equal to the heat, Q, plus the work, W, done on the system. Okay? And then if you really remember your thermodynamics, then you'll remember that there's a quantity called the enthalpy, which is usually symbolized in physics with a delta H, that's equal to some of those quantities above. Okay? So that's our Gibbs free energy. Now, when you're making nanoparticles, you could assume that things are happening a few ways. You could do like a chemical vapor deposition in which you're depositing nanoparticles on a surface, you're flowing a vapor over the surface, and a chemical reaction takes place and the little nanoparticles grow on the surface that way. You could do a wet chemical technique where you're mixing things together in solution and the nanoparticles crystallize out of a liquid solution. You could imagine that you have a molten material and you're trying to get the little nanoparticles to form within the bulk of the molten material. So there's a number of different scenarios that you could picture. Okay? But in any case, let's assume that you're forming these nanoparticles in some way. Let's assume for now that it's within a liquid. And let's also assume that these crystals are spheres, just for the sake of simplicity for the formula. Okay? All right, so you've got a couple of contributors to your Gibbs free energy. All right? These can be from the volume. You're going to have a certain volume Gibbs free energy, and you're going to have a certain surface Gibbs free energy. All right. The free energy difference between the solid and the liquid phases in the bulk on a per unit volume basis is your volume free energy, which here I've written as delta G sub nu. Okay. If the reaction is favored, in other words, if it's favored for the particle to become a solid from the liquid, then of course that means that delta G is going to be less than 0. It's going to be negative. Okay, so let's assume that the energy is negative during solidification. So the total Gibbs free energy should then be proportional to the volume of the material. So your total Gibbs free energy due to the volume is going to be whatever your volume free energy on a per unit volume basis is, that delta G nu, times your volume. And since we're assuming that you're getting spherical nanoparticles, your volume is 4/3 pi r cubed. Okay, so that's our volume free energy from the Gibbs. There's also going to be a different energy associated with the surface of the crystal. We talked about this, remember? Your surface atoms have a different potential energy than your bulk atoms, okay? And this is because the surface atoms are bonded to fewer nearest neighbors, or their coordination number is lower. They're bonded to fewer atoms than the bulk, okay, which raises their energy compared to those bulk atoms. Now, Since the surface atoms have a different energy than the bulk, this is often referred to as a surface tension in a liquid or a surface energy in a solid. Either way, it's symbolized with the Greek letter gamma. And this energy is positive because it takes energy to form a surface. The units are going to be newtons per meter or joules per meter squared for your surface energy or your surface tension. Now, your total surface free energy for the Gibbs from the surface should be your surface tension or surface energy times the total surface area. So delta GS, your Gibbs free energy due to the surface, is going to be, for a sphere, 4 pi r squared times gamma. All right? Now, this Gibbs is going to be a positive number, whereas the bulk Gibbs is going to be a negative number because it's favored to form a solid. But it takes energy to form a surface. You can think of surface energy and tension in kind of a more fun way if you want. It's what provides the resistive force during the expansion of a surface. So when you're trying to blow up a balloon, when you start blowing up that balloon, you're going to have to really blow hard and put a lot of work into the system because the balloon wants to stay tight and stay together, and it resists that expansion. Okay, so that's an example of a surface energy. Surface tension in liquids pulls the liquid particles together. Okay, so it's what causes capillary forces in liquids, for example, like water. And the high surface tension of water also allows little insects to skate or walk across the surface. And you've probably seen this if you've been out near a river lately. Now, if you look at your Gibbs free energy, the competing effects from the surface, which is indicated here in red, that 4 pi r squared gamma, and then the negative Gibbs free energy due to the bulk for the volume is 4/3 pi r cubed times that delta G nu. Okay, and you can see that there's a competing effect. So as the crystal grows, the surface area to volume ratio is going to rapidly change. We talked about that in one of the last online lectures. For small crystals, that surface energy term is going to dominate. But for larger crystals or going towards the bulk, your bulk Gibbs free energy is going to dominate. So when you add those two terms together, you'll get your green curve here. It'll go up, it'll come to a peak, and then it'll drop back down. Okay, that's what happens when you sum them up. There's going to be a critical nucleus or a critical radius, and then when you're less than that critical value where the peak is, when you're less than that, it's going to want to shrink the crystal and make it go away, and if you're on the other side of that, it's going to want to grow that crystal to decrease the energy. So this right here, this curve right here, is one of the big reasons that nanoparticles are different. See, because if you form a nanoparticle, you're forming it with a small radius, okay, which means that it's going to have a higher Gibbs energy than the bulk by a lot because it falls off here, right? You want to lower your energy. I mean, the whole system that we have here is based upon getting to the lowest energy state possible. And of course, that's going to make them more chemically reactive because they're going to want to react with things and pull that in. And it also affects a lot of other properties like the melting point. So for example, this is from your book. If you look at the surface energy of a calcite particle and you plot the surface energy in joules per meter squared versus their size, okay, then you can see that the surface energy is a lot larger for those tiny little particles than it is for the bulk, all right? So it drops rapidly as you go up in size. And nanoparticles can have dramatically different melting points compared to the bulk. You can plot the melting point change, which I do in the next slide, but the melting point change is going to be inversely proportional to the radius of the particle according to this equation here. Delta theta, which is the change in the melting point, is equal to 2 times the bulk melting temperature T sub m times the surface energy gamma divided by the density rho divided by the radius of the particle r, and then divided by the latent heat of fusion. Okay, remember the latent heat of fusion is from physics 1150, 1151, your introductory level physics class, and it's the amount of energy that it takes to change phase from the solid to the liquid on a per unit mass basis. So now if you plot this out for gold, the melting point of bulk gold is 1337 degrees Kelvin. The latent heat of fusion of gold is 63.7 kilojoules per kilogram, and the surface energy gamma of gold is 1.5 joules per meter squared. So since you've got your bulk melting point up here, so here it goes as your radius, you're getting to the micrometer range up here for your radius, all right? And that puts you over here on the right, which is near the bulk melting point of gold. But you can see that as you shrink that radius down to the nanometer scale, it drops off really rapidly. Your melting point really dramatically drops, okay? So that shows you how dramatically the size of the particle can affect the melting point. And that's because of the domination of the surface, right? The surface energy is such a huge factor there. It would rather just melt and dissolve and not be a nanoparticle anymore rather than have that surface energy, okay? Now, it also causes issues if you're trying to make nanoparticles. So when you're making solid nanoparticles, you're going to have to stop or cut off that crystallization process. Otherwise, your nanoparticles are going to continue to grow because it's energetically favorable for them to do so. There's a couple of mechanisms that happens in, and one's known as Ostwald ripening, okay? Ostwald ripening is when larger particles are going to grow and form at the expense of the smaller ones. Basically, if you think of it, let's say that you have you're doing a wet chemical method for making your little nanoparticles. So you're stirring things together and the little nanoparticles are starting to crystallize and form due to some chemical reaction, all right? So let's say they're forming like that, all right? Well, what happens is you've got atoms moving around within your solution in the vapor or in the liquid or whatever, right? So they're diffusing, they're moving around, and this happens kind of randomly, all right? But your bulk particles, right, when you add atoms to those, that's energetically favorable. And so even though particles are walking around all the time, entering and leaving particles kind of spontaneously, when an atom or molecule sticks to a big particle, it's energetically favorable for them to do that and for them to stay there. And so they're going to leave that particle at a lower rate than tiny little particles, in which it's energetically favorable for the particle to just go away, okay? So they have a larger rate of loss for the particles that they take on, the smaller particles do, than the bigger particles, and in the end you just end up with a whole bunch of big particles. That's Ostwald ripening. You also have the effect where these little nanoparticles like to stick together when they encounter one another. And this is known as coalescence, or sometimes known as sintering, okay? In coalescence or sintering, the nanoparticles actually touch each other for some reason, and because it's energetically favorable, they stick, okay? It's energetically favorable for the particle to be bigger, and so they stick together and then come together, stick, and stay in a big particle. That's energetically favorable as well. It's not the same as Ostwald ripening. Ostwald ripening doesn't require direct contact between the particles, and coalescence and sintering does. So lots of times if you're trying to make a nanoparticle, it's tough because the big particles are energetically favorable. And so if you're not careful, if you don't stop your reaction at exactly the right time, you're not going to get nanoparticles anymore. You'll get big particles, micro or bulk particles. So in order to stop this, scientists often add a capping agent, what's known as a capping agent, to stop the growth of the nanoparticle at a desired size. And this helps prevent Ostwald ripening, okay? So lots of times these capping agents are organic molecules of some sort. And let's say you add this organic molecule to the reaction in your wet chemical method at a specified point in time. And there's all kinds of recipes out there in the literature for how you do this, and different capping agents for different nanoparticles. Okay, so if you Google it right now, if you go on to Google Scholar or whatever else, and you look up capping agents, you'll find a ton of papers. All right. So what happens is it reacts. Your organic molecule, usually organic molecule, is then going to react with the surface of your nanoparticle and stick there, and that passivates the surface, okay? So it stops the reaction from continuing. Also, sometimes they'll add what's known as a stabling agent to prevent coalescence or sintering of the particles together. So for example, especially if you're going to keep your nanoparticles in a liquid solution, the chance that one nanoparticle would run into another nanoparticle is pretty high. Okay, so they're going to bump together, and then they would tend to coalesce or stick. So lots of times the scientists, especially in liquid solution, will add what's known as a stabilizing agent so that when the two particles meet each other and bump together, they don't stick permanently together. Lots of times your capping agent can be the same thing as your stabilizing agent, and then you only need to add one chemical, and so that's good news. So here's a little picture of that. This is from a paper, a 2012 paper by a research group that was making some magnetic cobalt nanoparticles. And so they wanted to passivate the surface, and so they added this HDA to keep the particles from clumping together in solution. All right, well, I hope you learned something from that, and let me know if you have any questions. I'll see you next time.